Hi everyone. In this video, I'm going to talk about amortized analysis of dynamic tables. We study how to obtain an amortized analysis for open addressing hash table with dynamic tabling. Python dictionaries are implemented this way, so we are going to focus on subtle points to go through this analysis. Our assumption here is that we will maintain the size of a hash table to be a power of 2 throughout the operations, initially set to 8. We expand it to a new table that doubles the size of the old if the load factor becomes 4/5 or higher after an insertion, and contrasts to a new table that halves the size of the old if the load factor drops down to 1/5 or lower after a deletion. We will ensure that the size of the hash table is at least 8 throughout. From the previous analysis, we know that regardless what probing function is used, as long as hashing is uniform, the expected number of probes is at most 1 over 1 minus alpha, where alpha is the load factor defined by L over M, where M is the table size, is the current table size, and L is the number of the current occupied slots, excluding tombstone slots. Note that if alpha is less than or equal to 4/5, then 1 over 1 minus alpha is less than or equal to 5. Now, in a sequence of n operations of insertions and deletions, the time to compute a hash value and update the load factor is independent of n. Hence, it's constant. It's a constant. So now let's look at key insertion. To insert a key, we need to compute the hash value of its key, which is a constant time, and find an unoccupied slot through probing for inserting it. Since the expected number of probes is at most 5, if the load factor doesn't exceed 4/5, and hash can be computed in constant time, inserting a key can be done in expected constant time. Let's call it C sub I with capital I, standing for insertion, which includes the time to compute the hash value and update the load factor. And so we have C sub I is greater than or equal to 5. But it's a constant. To delete a key, we need to compute the hash value of its key and search for its location using open addressing through probing to tombstone the item, that key. Then, similar to the above analysis, deleting a key can be done in expected constant time. Let's call it C sub D. Now let C be the maximum of C sub I and C sub D. Hence, we have C is greater than or equal to 5. Next, we're going to define our potential function, phi of D sub I, depending on the current load factor after the i's operation. If it's greater than or equal to 1/2, then it is equal to 3 times C times 2L sub I minus N sub I. And then if the load factor is less than 1/2, then it is equal to this form. 3 times C times, left parentheses, N sub I over 2 minus Li, right parentheses. And here, D sub I is the hash table after the i's operation, and small n sub I is the size of the current hash table, and L sub I is the number of occupied slots in DI. And the load factor alpha of D sub I is equal to L sub I over N sub I. Because we initially set the table size to be equal to 8, so that N0 be equal to 8. And then it's straightforward to see that phi of D sub I is always greater than or equal to 0 for all I, because we are going to look at this depending on the load factor, so we can do a straightforward verification that this is going to be true. And then initially, phi of D sub 0 is equal to 0 because initially there isn't any occupied slot where L sub 0 is equal to 0. Hence, this potential function is legitimate. So let's look at insertion. So suppose the i's operation is insertion. Now that first we know that the following situation can never occur, which means that before the insertion, the load factor is strictly less than 1/2. But after the insertion, the load factor is at least 4/5. It can never happen because the size of the hash table is always a power of 2, and then the size is at least 8, and so that obviously when the size is greater than or equal to 4 is also true. So this can also be done pretty straightforward, pretty easily. So now the amortized analysis is actually a case study. So we're going to look at different scenarios of the load factor before and after insertion, and also before and after deletion. So there are a number of cases that we need to look at. So let's look at the first case. Case 1. The load factor before the insertion is strictly less than 1/2, and after the insertion, its load factor is also strictly less than 1/2, and hence no expansion occurs. And because of the condition of the load factor of both load factor is below 1/2, so we use the same form of the potential. So we take the difference, and C sub I is the actual cost, the expected actual cost. So C sub I is less than or equal to C, and then you can see here, because there's no expansion, so N sub I is equal to N sub I minus 1, and L sub I is equal to L sub I minus 1 plus 1. So we do some straightforward manipulation. So this cancel out, And then this minus Li is actually equal to minus Li minus 1 minus 1. And then you'll have this negative. So this negative becomes negative. So that is plus. So this gets canceled. We got 3c. So that means we got a negative 3c. So this is less than 0. So it's a constant. Okay, so the next case is before the insertion, the load factor is strictly less than 1/2, but after the insertion, the load factor becomes at least 1/2, but it is still less than 4/5. Hence, in this case, no expansion occurs. And we still have that because of no expansion, n sub I is equal to n sub I minus 1, and Li is equal to Li minus 1 plus 1. And because of this, before the insertion, the load factor is below 1/2. So we have L sub I minus 1 is less than n sub I minus 1 over 2, which is equal to n sub I over 2. So then we can compute the expected amortized cost to be. So this is the actual cost, and this is the difference between the potential of before and after the insertion. And because of the boundary condition, so for the phi of d sub I, we use this form of the potential, and for the phi of d sub I minus 1, we use this, and then we just do some manipulation and then figure out what it is equal to. Okay, so quickly, so we know this is a 6c times L sub I minus 1. And then the Li is equal to L sub I minus 1 plus 1. So we got this actual 6c comes in, right? So this is from here going in, that's 6 copies. And then there are 3c, so this is a negative ci, and then this is 3c I over 2. Now remember, this ni is equal to ni minus 1, and then this c going there, so you got plus. So what we have, and merge c and 6c, so we got 7c. We merge 6cl sub I minus 1 with 3c sub 3cl sub I minus 1. We got 9cl sub I minus 1, and then merge these two together. So we get negative 9 over 2 c sub ni. And because earlier we said that L sub I minus 1 is bounded above by n sub I over 2. So we get this. So these are canceled. So this is equal to 6c. And that is bounded above by a constant. So this is good. So now let's look at the next case. So the next case is that before the insertion, the load factor is at least 1/2, and after the insertion, then obviously it becomes strictly greater than 1/2. The load factor becomes strictly greater than 1/2, but the load factor is still less than 4/5. Hence, there is no expansion. So as before, we have this condition. N sub I is equal to N sub I minus 1, and L sub I is equal to L sub I minus 1 plus 1. Then the amortized cost is the actual cost of inserting this P, which is a C sub I, plus the difference between the potential. And then because both of the load factor is at least 1/2, so we use the same form, which is simpler. So we do the calculation. So this is a 6cl(i) minus 1, and then plus 6c, okay, and then minus 3c n sub I, And then this is minus 3 times, so 3 times 2 is 6, so minus 6c L sub I minus 1, and then this going in, so this is 3c N sub I minus 1. So now let's see that this gets canceled, this gets canceled, so merge C and 6c, we get 7c. So that is still a constant. So the expected amortized cost is bounded above by 7c. So now let's look at the last case for insertion. So before the insertion, the load factor is at least 1/2, but less than 4/5. But after the insertion, the load factor is greater than or equal to 4/5. Okay, so now in this case, there is some subtle points that I would like to make sure that I make it clearly. So for this D sub I, so we actually have two versions of it. One is before expansion. The other one is after expansion. So before expansion, we know that N sub I is equal to N sub I minus 1. And after the expansion, we know that N sub I, so this is N sub I is equal to 2 times N sub I minus 1, because expansion means we will double the old table, double the size of the old table. Okay, so that means that in order to not to confuse ourselves, so before the expansion, we are going to use instead not use N sub I, but I use N sub I minus 1. Then after the expansion, I'm going to use this. Hence, I have the load factor alpha of D sub I. Also, I have two versions. So this is before expansion and after expansion. So before expansion is going to be L sub I over N sub I minus 1. And then after the expansion is going to be L sub I over 2 times N sub I minus 1. So this is a subtle point. All right, so once we have made this clear, then we know that after the insertion, the load factor, which is L sub I over N sub I minus 1, is greater than or equal to 4/5. And this is still the same because of the insertion L sub I is equal to L sub I minus 1 plus 1. And the actual cost of inserting or expansion, right? So the actual cost of expansion is the following. So first of all, we need to do a table lookup to find out keys that are not tombstoned. So because the table size is N sub I minus 1, you would expect this much time. And then for each of on tombstone key, we need to move over to the new table following the open addressing procedure, which means that we're going to compute the hash value of each such key. Then we're going to insert it into the right place with certain so from left to right, for instance. So then we have L sub I many untombstoned keys, and for each such key, we're going to insert it to a new table that would take C sub I time. Hence, we would expect that C sub I is less than or equal is less than N sub I minus 1 plus CI Li. It could be less than or equal to. So let's just make it equal. All right. So there's another subtle point here. So we need to do some calculation is that we assume now, since we assume that throughout the operations, the size of the hash table is always at least 8. Hence, 2 times of n sub I minus 1 is at least 16. Now remember, we have this before the insertion, which is L sub I minus 1 over n sub I minus 1 is less than 4/5. And after insertion, we have this. So hence we will do a simple manipulation. Then we figure out the after. So this is after expansion. The load factor is L sub I over N sub I, so which is equal to this. And then the first part is less than 4/5 over 2, so which is less than 2/5. And then the second part is 1 over 2 n sub I minus 1, so which is less than 1/16. So you add them together is less than 1/2. Okay, so this is another subtle point. So that means that now we figure out that which potential form we're going to use. So after the expansion, so we are going to, this load factor becomes less than 1/2. Hence, we are going to use this form, and then before insertion, before insertion, we use this form because it is greater than 1/2. It is at least 1/2. All right. So now we do some. So this is the actual cost. So now let's do some manipulation here. And so here n sub I minus 1 plus. So this is C sub I is less than or equal to C. So you now remember Ni is equal to 2 times n sub I minus 1. So that's why we get this. And then so this goes in, we get this. And this goes in, we got 6 copies. This goes in, the negative becomes positive. So that's what we have here. So now let's merge similar terms. And then we get 3Cni minus 1, 3. So we got 6Cni minus 1. And merge these two. We got negative 2C times L sub I, and then copy this one down. So now we are here. Okay, so we're gonna write Li, which is L sub I minus 1 plus 1. So we get negative 2C, so which is negative 2C, and this becomes negative 2C. Okay, so this negative 2C will be merged, which is negative 6C, and we got negative 8C times L sub I minus 1. Then we got a negative 2C here. So that's what we get here. So now we're here. So now let's look at, remember earlier we said that L sub I minus 1, the load factor before is strictly less than 4/5. Okay, so this is a 4/5. And then we have And after is okay. I would need to use this rather than another one. So I'm going to fix this here. So I'm going to pause and then I'm going to fix it. I'll come back. Okay, so I have fixed that uh, error. So now we are going to look at this again. So so we already saw, so this earlier will be minus 6c L sub I minus 1. So I change L sub I minus 1 to L sub I minus 1 because Li is equal to Li minus 1 plus 1. So you move this over, so that is minus 1. So we got that. Okay, so then we merge this part so that like I have a negative 8 times C times L sub I, and then this negative becomes negative becomes plus, so we got plus 6C. So now we are here. So we are here. So then, and because of the low factor after after the insertion before the expansion, so we so that is that. So L. Remember earlier we said that L sub I over N sub I minus 1 is greater than or equal to 4/5. Okay, so then the negative. So the negative then becomes less than or equal to negative 4/5, and then 4 times 8 is equal to 32. So that's why we get this. And then plus 6c. Okay, so now we merge these together. So 6 times 5 is 30. So we got a negative 2c here. And then we put this in this form. So it becomes 5 minus 2c over 5 times n sub I minus 1 plus 6c. And then c is greater than or equal to 5, and obviously is greater than 5 over 2. So which means then 5 minus 2c is straightly less than 0. So the whole thing then is less than 6c. So the expected amortized cost is bounded above by 6c when the expansion occurs. So that is the amortized analysis of the of an insertion. Now let's look at deletion. Suppose that the i's operation is deletion. Okay, so again, we know that the following situation can never happen. So which means that before the insertion, the load factor is at least 1/2, but after the deletion, before the deletion. So before the deletion, the load factor is at least 1/2, but after the deletion, the load factor suddenly drops to below 1/5. It cannot happen because we assume the table size is always the power of 2, and then the table size is at least, well, when this is true actually, when the table size is always at least 4, but we assume it's always less, at least 8. So this is can never happen. So we can do a straightforward uh, a verification to confirm that this is the case. Okay, again, we are going to do case analysis. by looking at all possible scenarios before deletion, scenarios of load factors before the deletion and after. So let's look at let's look at case number 1. So before the deletion, the load factor is less than 1/2, and after the deletion, obviously the load factor is less than 1/2, but we assume that it's now still greater than 1/5, and hence no contraction occurs. And so in this case, we have, because of no contraction, so n sub I is equal to n sub I minus 1, and L sub I is equal to L sub I minus 1 minus 1, and both of the load factor is less than 1/2, hence we know the form of the potential, which is the same. Okay, so C sub D, this is now the actual cost of deleting an item. And then, so this is less than or equal to C, and this is the form. So now we do a straightforward manipulation. So this and that canceled, and this is negative. L sub I, now remember L sub I here is L sub I minus 1 because of the deletion. So you'll get minus 1 here, and then negative u here, so that becomes plus. So that's why we got 3C plus. Okay, the other parts cancel. So that is 6C. So the expected amortized cost is less than or equal to 4 times C, which is a constant. So the next case would be before before deletion, the load factor is less than 1/2. And after the deletion, the load factor drops down to 1/5. In this case, contraction occurs. So again, as before, so for this NI, we have 2 versions. So this is a before contraction and after contraction. So before contraction is equal to n sub I minus 1, and after contraction is only half of it. Okay, so this n sub I minus 1 over 2. So likewise, we can look at the load factor we have before and after. So we got 2 versions of it. So we are going to use n sub I to denote the size of the hash table after the contraction. To avoid confusion, so before contraction, we are going to use n sub I minus 1. So that's what we are having here. So after the contraction, so n sub I is equal to n sub I minus 1 over 2. And L sub I is equal to L sub I minus 1 minus 1. And then we have before contraction, the load factor, which is L sub I over n sub I minus 1 is less than or equal to 1/5, and hence the contraction occurs. And then, so that means that we have this L sub I is less than or equal to 1/5 times n sub I minus 1. Hence, we can look at the load factor after the contraction. So which is L sub I over n sub I. So we do a simple manipulation, and that gives us the result, which is less than 1/2. Hence, we know the form of the potential, what form of the potential to use. both of the load factor is less than 1/2, so we are going to use the same form. And then now this time uh, we have the cos of the uh, division. So first of all, we got the cos of a C sub D because we have to identify the item to delete, given the key, so we have to find it. And then we have to move things over, so this part is the same. So we have to search for the entire list and to find out which keys are on tombstone so that we need to move them over. So when we move them over, we have L sub I keys to move them. So then for each such key, the expected cost is C times I, including the probing, including the other necessary steps. So which is the actual cost here? So C sub D plus N sub I minus 1 plus C sub I times Li. So this is this form. Okay, so C sub D, C sub I is less than or equal to C. So now we are going to unify this constant to be C. And so now let's look at this term. So N sub I is equal to N sub I minus 1 over 2. Now remember, we always use this as the size after the contraction. So then we get this. Okay, so this is straight, this is straight, this is straight. Okay, so now we merge similar terms. And so this term and, sorry, too quick. So let me change that. So we got 2CL okay, and now Li is Li minus 1 minus 1. Okay, so so I got these two merged. Yeah, you can do your own calculation. So which is, so this is 3C, so this is 3C, so this is 3C. And then, so this is a negative, so this is a plus. Right, so, and so we got -2, which merged with that. And we got 3C extra, that's where it comes from. And this is the same, didn't change. This is the same, didn't change, the same, didn't change. So we are here. So we are here, and then we merge this. So that's 4C. And then we are going to merge this. So that's 1C. This comes down. And then we're going to merge these two. So that is, so if you do that, it becomes 6. So that's 3C over 4. So it's a negative. Okay, so, and then, and now remember that Li before, right? So before the so this is the after, right? So this is after the insertion. We know that this is less than or equal to 1/5. Okay, so that's what we have here. Okay, less than or equal to. So we do this calculation. So you simplify this. So that we get, yeah, we got this. So know that this C is actually greater than or equal to 5 in our case. And this obviously okay, but C greater than or equal to 5, obviously this is negative, right? So it's much easier to see, much smaller term. So this whole thing is negative, so it's less than 4 times C. So the expected cost of contraction is less than 4C after deletion. So now we are going to look at the next case, so which is before deletion, the load factor is at least 1/2, and after the deletion, the load factor becomes less than 1/2, but this is still greater than 1/5. Okay, so we're assuming it's a low contraction, and so in this case, we figured out it's no contraction. We have n sub I is equal to n sub I minus 1. We have a deletion, so that's Li is equal to L sub I minus 1 minus 1. So because of this, we know which form of the potential to use. All right, so this is the load factor is at least half, and this load factor is straightly less than half. So we use the different potential form. And now let's do some manipulation. So we do a straightforward one. So take the 3C out. So we got, so this here, and then we expand L sub I, which is L sub I minus 1 minus 1. So we get that. And then this is here. So negative becomes plus. So then you can see here, we got 3 copies, negative 3Li minus 1, and then this is a plus 1, and then this and that merge, so that's 3/2. Okay, so here we know that L sub I minus 1 before deletion, so which is this, which is we assume is greater than or equal to 1/2. So the negative becomes less than or equal to 1/2. So that's what we have here. Okay, so this gets canceled. So that's 4C. So which means that the expected amortized cost in this case is bounded above by 4C, which is a constant. So we are down to the last case. So the load factor are both greater than or equal to 1/2, but after the deletion, the load factor is still, I'm sorry, so this is no contraction. So no contraction because it's greater than 1/2. So then we know which form of the potential to use. So this is straightforward. So we can see here, and so this cancel. Okay. So this canceled. Oh no, not that canceled. So this canceled because minus this cancel, and L sub I is equal to L sub I minus 1 minus 1. So for this part's canceled. So we got this part, which is 2 times 3 times C, so that's 6C. So it's actually negative 6C. So then this is less than 0. Again, the amortized cost is less than 0 in this case, so which is bounded above by a constant. So in conclusion, then we have obtained a detailed amortized analysis of dynamic tape. Okay, so for n operation of insertion and deletion, we know that the amortized cost for each insertion and deletion is bounded above by a constant, and hence the time to execute the entire sequence of n operation is linear, okay? Expected linear time. This is the end of this video. Thank you for watching.